Hello and welcome to Mathematics with Simon. Today we're going to look at a half plus a quarter plus an eighth plus a 16th plus a 32nd plus ... the sequel. So last time we found a really pretty way to work out what this infinite sum is. We basically times it by 2. So when you times it by 2, the half goes to 1, the quarter goes to a half, the eighth goes to a quarter. Then when you subtract the top row from the row below, the half and the quarter and the eighth and the 16th all cancel out. You just get left with 1. So 2x minus x is x. And then on the right hand side, you just get 1. So it immediately just cancels to x equals 1, which is the answer. But Andy Robertshaw and Simon Howard both made some really good points that this isn't quite rigorous. Because strictly speaking, not just strictly speaking, but we did not define a sum with an infinite number of terms. We didn't say how that works. Now, you might ask, well, how much trouble can this cause? Well, quite a lot of trouble. I mean, so x equals 1 plus 1 plus 1 plus 1 plus 1, ... plus forever. What's that going to be equal to? And some people might say infinity. Then other people might say, well, is infinity a number? Is it an idea? Is it a concept? That's another video, very interesting video. What about this? X equals 1 minus 10 plus 100 minus 1,000 plus 10,000 minus 100,000 plus a million. I mean, where's that going? It's wobbling all over the place. It's sort of diverging to positive infinity and minus infinity at the same time. Each term changes the sign. This one's fascinating. X equals 1 plus a half plus a third plus a quarter plus a fifth. So this one is fascinating because it doesn't converge. So this gets bigger and bigger and bigger and bigger. So given any number, this sum will exceed that number. So again, it actually adds to infinity, even though the individual terms are getting smaller. And one of you clever people can explain in the comments why that's happening. To prove, how do we prove that this never converges? It's a beautiful, quite an easy proof actually. So these infinite sums cause so much trouble. I mean, so much beauty, so much interest, so much intrigue, but a lot of trouble. So we're not going to have an infinite sum. We're going to go for a finite sum. So for instance, we could say x equals a half plus a quarter plus an eighth up to 64, but then stop and not keep going. One way of writing this is x equals 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2, 4, 2, 5, 2, 6. And then 2x equals the expression given here. And then when you take one from the other, when you take x away from 2x, you just get 1 minus 1 over 2 to the 6, which is quite small. And this is the clue as to how, by taking these longer and longer and longer, x is going to get closer and closer to 1. So we're going to use n. So we're going to call this xn. xn is this sum from a half up to 1 over 2 to the n. So 2xn goes from 1 to 1 over 2 to the n minus 1, because when we multiply by 2, we cancel one of the 2's in the denominator. And then we work out xn by subtracting the middle line. We take the middle line and we subtract the top line. So we subtract the top line from the middle line. That gives us xn. And we get a 1 from the 2xn, and then we get minus 2 to the n from the xn expansion, and all the other terms just cancel. So xn equals 1 minus 1 over 2 to the n. And as n gets very big, 2 to the n gets very big indeed, and 1 over 2 to the n gets very small. So this gets closer and closer and closer to 1. The exact precise phraseology is to say, given any epsilon, there is an n such that 1 minus xn is less than or equal to epsilon. So we can make the distance between 1 and xn really tiny by making n big. So we just need to choose n so that 1 over 2 to the n is less than or equal to epsilon. This gets really, really small. Or put it another way, when you just go through the algebra, n has got to be greater than or equal to log 1 over epsilon divided by log 2. So once you've got an epsilon, you can work out an n that will satisfy this. So this shows us that this series here, this infinite series, converges to 1 because as these finite expansions get bigger and bigger and bigger, they get as close to 1 as we choose. They get arbitrarily close to 1, which means the series ultimately converges to 1. I hope you've enjoyed that. It's 11:30 at night. I've just walked the dog. I've really enjoyed doing this. You're very welcome to subscribe and hit the notification bell. There will be more stuff coming. One of the things I might send is a proof that this works for all geometric progressions where the common ratio is less than 1. But I'd love to hear your ideas, and most of all, I hope you enjoy your mathematics.